Great. Cool. Thanks a lot. So today I will talk about and present to you our recent work that we published at ICML. I will try to guide you through our understanding of loss landscapes and weight structures in neural networks and how we can exploit this to perform parameter recovery or reverse engineering of weights from neural networks that we can only query. And then I will introduce briefly our algorithm, which is called expand and cluster. So let me jump straight into the setup. I'm interested in parameter recovery, which is basically trying to give an answer to this question that's in the red box. Can we identify the weights of a neural network by probing its input-output mapping? And to make it a bit more concrete, the setup is the following. I have a deep feed-forward neural network, out of which I have no information about how many hidden neurons are present in the hidden layers and what are their connections. So what are the weights that connects two neurons? The only thing I can do is give some inputs to the network and record the outputs. So basically I can only query this network. And now the goal and the question of this talk and my paper is, can we actually recover the parameterization of it? And what are the conditions? So we can already start to give it a try. A very first naive approach. This is the network I presented you before. Sometimes I call it the black box network. Sometimes I call it the teacher network. Sometimes I call it the target network. In this case, let's call it teacher. We can collect a data set of queries from this teacher, let's say n queries, and we can use them to teach another network, a student, to learn them. And let's say for this simulation, for this slide, I cheat already. So I open a little bit the black box and I count how many neurons are present in this teacher network, such that I can construct a student network of exactly the same size of the teacher. So teacher and student are of the same size and of the same architecture for the moment. The only thing I want to do is to recover the connectivity. So this I still don't know. So I just come up with a random initialization for my weights. I code mean square error loss between the output of the teacher and the student. And then I press a button, I run gradient descent, and I try to tune my parameters such that we can minimize this loss. We can do it. This is the result. So, well, this is a bit arbitrary. It's something around 10 to the minus 2 mean square error. I can tell you it's bad. I'm not happy. And I'm not happy because I know that there exists a solution which lies at 0. So it should be here at minus infinity in this graph. But this is not happening. And maybe, I don't know, probably we were a little bit unlucky. We can try again. I can run the animation and I can try a few seeds, many more seeds, many more initialization. And it turns out that they all get stuck way above, for example, 10 to the minus 3 of loss. So there's something not clear. It's not straightforward to just train a student to learn the queries of the teacher. And in this setup, I have lots of queries. So it's not a data problem. I have really a lot of queries. And when I analyze these dots, these solutions, I find that they're not at all sharing any knowledge about the teacher parameters. So I will try to give a solution to this dilemma, to this problem. But first, maybe let me start with some motivation about why are we interested in parameter recovery. I think it's a great framework to understand loss landscape and weight structures, both from a theoretical point of view, but also from numerical point of view, where you can do experiments and really verify if your understanding is actually correct or not. And throughout this talk, I will touch a few key concepts of loss landscapes that people might be interested into, and there's lots of literature about them. Something about local minimum saddles that we can understand from this setup. Something about properties of overparameterization. So overparameterization has been shown in many ways to be helpful in learning, and theoretically, some results have led to speculations about how training should behave in these teacher-student setups, for example. And we will confirm empirically these speculations and show more evidence for them. And moreover, of course, to perform parameter identification, we need to understand all of the symmetries in this weight space. And this is also uh, interesting research that is being going on for a while. Maybe on the more practical side, parameter recovery, I think it's interesting because once you're able to do it, you're effectively stealing a network. So imagine a network which is computing, I don't know, it's performing a service for a company under an API, and there is intellectual property there. And if you're able to perform a model stealing attack, so recover the parameters of this black box network, then you'll be able to effectively steal some intellectual property. So this can raise, of course, security threats and ethical concerns. So this is something we can look into and be careful about. And maybe more in detail, this is already a niche of machine learning, these model stealing attacks. And even more niche is the subgroup, the subset of model stealing attack that look at exact recovery. So this is what we want to do. We want to have an exact recovery of all of the parameters of the network, which is the hardest problem. You can actually do other types of attack where you can try to extract the size of the network, size of some layers, some hyperparameters, or come up with an approximation of the model that you want to steal. But in this case, we're actually looking at exact parameter recovery. And just to reiterate, I don't just want to learn a data set with a specific accuracy. I want to learn a network that solves the data set in exactly that specific way. So that's why we believe it is the hardest problem. And it's not only us, there's other people as well. So maybe more practically, once you manage to steal all of the parameters, you have a copy of your target model, and then this can unlock even stronger adversarial attacks, which are called white box attacks. Those are the attacks that are developed by having knowledge of the weights or having the ability to compute gradients, for example. So if you have a malicious agent that wants to do something bad and has a copy of your network, then they can also actually implement some white box attacks, and this could be bad. On the good side, state of the art in exact model extraction is not a concrete threat today. Here I'm citing a few papers, and actually there's not that many more, and people in the field usually reconstruct networks of maybe 100 or 200 neurons maximum, and maybe 2 to 3 hidden layers of size. So they're relatively small networks, and I don't know if they're actually used in practice, so that's why I say it is not a concrete threat. And for the moment, all of the papers I'm citing, they actually share a very similar technique that only works on ReLU networks, while here today we will show something that works for any activation function, any common activation function. Maybe, sorry. One thing that I didn't mention is that, of course, if you don't aim at practically at stealing exactly a model, but you want to build a sort of approximate copy, then you better do that and not steal the full parameter space, because it's going to be more costly and more expensive. But there are some types of systems and some types of networks that one would like to really characterize fully because they cannot be approximated or retrained. And one of these systems is actually some circuits that are present in our brain. So as Olga said before, I actually did a master in neuroengineering, but I come from a computational neuroscience lab. So we're actually also interested in the brain and brain circuits. And this is a bit more tangential to what this reading group is interested in, probably. But very briefly, in neuroscience, there are three main types of information that one can record from the brain. One is neural activity, so neural recordings. One is behavior, so whatever your circuit is actually outputting and what can you observe that the agent is doing. And the third type of information is neural connectivity. So if I would like to understand the brain, I would like to have in my hardware, in my hard disk, as much information about these three types of quantities altogether. And usually the first two are relatively easy, technologically easy to record and collect, while the third one is a bit harder, especially because when you collect it, then the brain is already destroyed. So I'm also interested in looking if there is a way to kind of recover some of this data from, which is quite sparse, from the other two. And yes, in a way, what I'm doing is trying to recover neural connectivity from neural activity, but we're looking into very simplified model, which are just artificial neural networks. So this is work in collaboration with Berfim Shimshek, Wolfgang Gersten, and Johan Ibrea, which are my co-authors. And everything I will talk about today is done in their collaboration. And I'll also talk about some of the previous work of Berfim to introduce the theory. So if there are any questions about the intro, maybe this is the moment to ask. Otherwise, I will go with the first approach. Actually, I have a question. What is going on here? Why do you think it's failing? Does somebody want to give a try? I think I already anticipated a little bit the answer. Yes, okay. So if nobody wants, I can try myself. Sorry, I'll put it here.
Too few minima, too many saddles, something like this.
So you say there are too many saddles in the landscape?
Maybe. Just
Yes.
give it a shot.
Yeah, I think it's a guess. I didn't say anything. So, so I think it's a good guess. I think I maybe at the moment we don't really know if there are saddles or not, but for sure we know that the landscape is non-convex. So we cannot really guarantee that we're gonna reach the global minimum, which is the point where we're at zero loss, right? So maybe we were unlucky with initialization and we landed in a local minimum. It can also be that, well, this is very simplified picture. I believe the picture looks a little bit more like this. It's still just a cartoon. And actually the picture is really bad in the sense that the loss landscape is high dimensional and it's very rough probably. So whenever you initialize something, you have a very low chance of landing close to the global minimum. But let's explore this further. Let's try to understand a little bit more. So now my slide is a canvas, and I have here in my space, it's parameter space, and I'm plotting the loss. I'm looking at a teacher of 4 neurons per hidden layer, and at a student who's smaller. So 1 neuron less in this case. So we know this student will have a minimum, maybe more than one, and it's most likely, so it will be at a higher loss, not zero, because they don't have the same capacity, and the student and the teacher is not compressible. So I'm looking at the minimum of an underparameterized network. Let's play a little game. We take this smaller student, we make it even shorter, and we look at this neuron here. And the contribution of this neuron is this input weight vector times the data plus bias, activation function, output weight vector, classic. And now we do an operation which is called neuron splitting. That means we take the original neuron and we split it into two without changing the function of the network. So this new neuron will have the same input weight vector and bias, so it will extract the same feature. And then the contribution of these two splitted neuron, represented by the sum of their output weights, will correspond to the original smaller student neuron, right? By doing so, in the student network I was showing before, we can maintain functional equivalence, meaning that I just duplicated these two neurons. The loss is going to remain the same because the function is the same. If you do a little bit of math, you realize that the gradient is also maintained. And which means that basically this point of a bigger network is still a critical point of the dynamical system, meaning that it's still a point of zero gradient. So if we go back to the canvas, I'm changing the title here and I'm changing the network. Now we're looking at loss landscape of correctly sized students. That is because I added a neuron, this split neuron, and this point that we were looking at before, it's not anymore a minimum, but it's a critical point of the same parameterized network, meaning that it's a point, again, at loss higher than 0, but the gradient is 0. I cannot really tell if it's a local minimum or a saddle. It could be a saddle. What I can tell for sure is that now the two networks are of the same size. So somewhere else in the loss landscape, there is a global minimum. Actually, there is more than one, many more, because I can just permute all of these neurons. I can just swap them, and the function will remain the same. It's just I will move somewhere else in the loss landscape, but I will keep the same properties. So the loss will be still 0. Funnily enough, one can do this game for all of the underparameterized student networks. And these underparameterized student networks will have a lot of local minima at different levels of losses. So basically, we know that in the loss landscape, there will be various levels of critical points that originate from underparameterized networks. And at the bottom, there will be a bunch of global minimum here. So generally, I think gradient descent has no problem in traversing the saddles because there is a zero measure space here where you can actually get stuck. Usually gradient descent with a little bit of noise, SGD, can usually escape all of these saddles. So this shouldn't be really a problem. I don't know. For the moment, it shouldn't really tell us much. But there is past work and ongoing work in our lab where we try to characterize what is the structure, the curvature of these critical points here. And this is a rough little model. It's not really what is happening, but you can see that what turns out by doing the math is that some parts of these critical points are actually local minima. So for example, these parts here are local minima, or you cannot actually escape if you do gradient descent because some direction has, they have a zero curvature, while some parts are actually saddle points. So not all of these critical points are benign in the sense that some of them actually they have a little basin of attraction. So the work of my colleague 3 years ago was to actually combinatorially count how many of these critical points are present. They're not points, actually, they are manifolds because they're also spanned by specific splitting that actually creates not points, but lines, but I'm glossing over this. But simply by doing a very careful combinatorial count, one can compute how many of these critical points are present as a function of the teacher size and the student size. So here I'm just plotting the ratio between student and teacher. So in this case, the student is always smaller than the teacher, but as it gets bigger, there will be more and more of these critical points, and they grow combinatorially. So this is given this formula here. And so this is our intuitive explanation of why when you train a student of the same size as the teacher, you very likely get stuck because there are combinatorially more critical points that are not at zero loss than global minima. So I hope this is clear. I will continue. But first, just
may I ask a short clarification question?
sure.
So a critical point is a what? A local minima of any type or a saddle? Is that
So a
correct?
critical point is a point of zero gradient. So it can be
Zero
both.
gradient, yeah, it could be anything. And if you go back to your this very nice 3D, yes, exactly this picture. So do I understand correctly that these bold kind of black lines, these are, oh no, these are not saddles. Okay, I see.
No, the saddle is here actually.
Yeah, exactly.
Yes.
Okay.
So this is just a model. It's not really what's happening in the neural network, but it's I think it's the smallest possible
Yeah, this is just an example, right?
visualization, right?
Yeah.
But it's a model of a function that has a line of zero gradient, right?
Exactly.
A splitting line that we had when you had this sum of two neurons. So there's one dimension of degeneracy. And depending on where you are in the line, you can get stuck because all the curvatures are positive or zero. or you cannot get stuck because there's at least one escape direction.
Right. And this type of picture, you say this is a critical point, or there are a bunch of critical points here, basically along this line.
The whole gamma,
The whole gamma,
here,
yeah.
it's all at zero loss.
Okay.
Basically, this direction, sorry, zero gradient. On this direction
Yeah.
is gradient,
Yeah.
this direction as well. Yeah.
So all these are critical points, basically.
Yes.
Okay, cool. Thank
So
you.
this is something you can find in neural networks, and we're actively exploring it. So if you're interested, in the future, we'll send a message.
Great.
Yes. Cool. So this is the picture. Lots of critical points. Some are bad, some are escapable. But there's many of them. So how do we deal with those? First of all, maybe let me be a little bit more rigorous. I just give you a little recap of the assumptions. So I tell you what I know of this setup. I assume I know the number of hidden layers. This makes my life a little bit easier. One could also brute force it, but I need to know the activation function for reconstruction to be possible. And also I need to know, or I need to have the input and the output layers that are fully observable. So I need to observe the full dimensionality of input and output, just to make it a little bit rigorous. We can go back to the picture and we can try a different strategy. We can make the student bigger. I think there's no surprise. People always make networks bigger because they should learn better, right? So we can expand the student and add more neurons than actually the neurons that are in the teacher. In this example, I will add 4 times more neuron than in the teacher. I can train again with gradient descent. 1 seed, 2 seeds, a bunch, many more. And you can see that actually the loss now is going considerably lower than before. So expansion works, right? Now I'm showing you another example where these are actually the sizes of the network that I tried. So with very small networks, you can actually reach basically machine error zero loss, which is this 10 to the minus 16 root mean square error. It would be 10 to the minus 32 mean square error by just doubling the layer size, or even multiply it by a factor of 4. So why does this work? Let's have another intuitive look at the loss landscape. Now we're looking at the point where student and teacher are of the same size. So this is the landscape. And there's a zero loss point. As I said, you can copy all the parameters of the teacher into the student, and then you get a zero loss point. And the student will have basically each of the neuron of the student will have to duplicate each of the neurons of the teacher. So there will be a one-to-one correspondence between the two networks to have a zero loss point, or at least to have this zero loss point. But we can play a game. We can look at the expanded landscape, but in a specific form. I want to add a new neuron in such a way that I don't change the function of my network. So this is the contribution of the new neuron. And I can add one and not change the function, so stay at zero loss, by just adding a neuron that does nothing. So output weight vector of 0. An arbitrary input weight vector, it doesn't matter what feature is extracted, as long as it doesn't contribute. Now I transform this point global minimum into a subspace, a hyperplane of global minima spanned by this d in dimension that looks like this. So by adding a neuron, which we call zero neuron, we effectively do not change the network function, but we are in a higher dimensional landscape. I can also add more than one neuron, a zero neuron group, as long as they extract all the same arbitrary feature and then their contribution sums to 0. And these are neurons that can happen at zero loss. Another point that you can find, which is actually connected, is the point where my new neuron that I add, this N neuron, is extracting the same feature as another neuron in the student network. So now they're basically split. And this feature was actually also the feature of the teacher, right? And the sum of the contribution of this neuron adds up to be the contribution of the original teacher. So if you take the contribution of the teacher minus the one that we already had in the student, it will add up to the contribution of the new network. So by doing so, there is a line of global minima again, which is spanned by the fact that these two neurons are actually copy of themselves, and they are both contributing to replicate one teacher neuron. And this we call duplicate neuron group. There could be even more than a pair. And lastly, there's another manifold, a manifold of constant neurons. So I can add a neuron that has zero input feature, so doesn't react to any input. It's gonna just output the same constant all the time, so this bias here. And then a bias can be accounted for in the next layer. And basically, I can maintain functional equivalence by adding a neuron that has a zero input feature. So by doing so, I can construct manifolds of zero loss that are actually connected in this parameter space. And well, the conclusion is that one can do this by adding one neuron and copying, sorry, let me just rephrase it. As you can see, maybe from what we see before, sorry, I can play this game many times by adding more and more neurons, and then I will have lots of combinations of these manifolds that can create. And they will grow combinatorially because they will grow also with the counting of the permutations of this neuron. So I can copy all of the different neurons of the teacher. I can always do these red manifolds and these green manifolds. So one can also count this, and that's what's been done in the past. And the more I add neurons, they maintain the function as zero loss, the more the amount of global minima grows. And if we take the ratio between the critical manifolds that I showed you before, which are also growing, by the way, and the amount of global minima that will grow as we add more and more neurons, there will be a tipping point very early when student size over teacher size is roughly 1.4, where the global minima will start to outnumber the critical manifolds. And by the time we arrive to factor 4, so the student is factor 4 bigger than the teacher, then we have combinatorially many more global minima than all other manifolds. So our claim, which is actually coming from the theory, is that mild overparameterization is enough. So just a factor 4 should be enough to train these big networks to a zero loss, just because of probability, just because there are too many global minima and very few critical manifolds here. So just to show a little example, this is a network, teacher network of size 30. I'm trying to learn it at different overparameterization ratios, right? This is one is the tipping point where the student and the teacher have the same size. And here I'm showing the various losses that I get from different seeds. And you can see that as I overparameterize more and more, I start to get global minima more and more with more probability. And it kind of looks like this picture here. Although it's very hard to translate number of manifolds into probability of reaching a global minimum or not. So again, we've shown that expansion works, but what about the weights, right? Now we have a student that is way bigger than the teacher. So we cannot really claim that we have performed parameter recovery. We just can claim that the two networks are functionally equivalent. So is there a mapping between the two? And is there a question from the audience? So if everything is clear, I will continue. And as I showed you before, if we look at the expanded loss landscape, we can see that there are only 3 types of neurons possible, or at least I want to claim that there are only 3 types of neurons possible that could happen in this landscape. The duplicate neurons that I showed you before, the zero neurons, again, that I showed you before, and the constant neurons. So if these are the only types present in this new landscape, then the goal would be to try to identify the duplicate neurons, which are the neurons that are actually copying the teacher weight vectors, these ones with the star, and get rid of all of the other neurons that are actually doing nothing, which are defined by these properties here. So their sum, output weight sum goes to 0, and their input weight vector is going to 0. So I mentioned that actually these are the only neuron types, but I didn't tell you why. There is a proof. It's called there's no new global minimum proof. But well, I'll just try to give you a little bit of an intuition. So if sigma is analytic and they have infinite even and odd non-zero derivatives, so a very specific condition, you can show that you can expand this the contribution of a single neuron in a power expansion, and then intuitively, as long as this power expansion has infinite coefficients, you will not be able to find a finite amount of student neurons that with different input weight vectors can actually match exactly this function for all inputs. So this is intuitively what's going on, but there is a proof that you can check. So basically, as I said, those three types are the only neuron types that are present in this loss landscape. As long as my activation function satisfies this condition, which is a funny condition. Actually, for example, the exponential function satisfies this. The soft plus sigmoid function satisfies this, but not the commonly used activation functions. So for the moment, we just stick to these weird activation functions. And well, now the question is, how do we separate duplicate and redundant neurons? So in ideal zero loss settings, zero groups and constant neurons are easily identifiable, right? Because I can just look at whether there are neurons summing to 0 in their output weights or equaling to 0 in their input weights and keep all the rest. But in practice, I can never train to exact zero loss. So with big networks, there's always numerical error. So I will never be able to filter out or find a specific threshold that can filter out some neurons and keep others. So it becomes a little bit more challenging. So the solution would be, let's cluster. Here I'm showing a very, very small teacher with just two neurons, number 1 and number 2. And what I want to do is I train not one overparameterized student, but n overparameterized students on this teacher. And then I will cluster their input weight vectors. So let's say I train at student network number 1. It learns to duplicate teacher neuron number 1, teacher neuron number 2. Then there will be a zero type neuron and constant type neuron. And then I can see different combination of these in different student networks that I trained. When I perform the clustering, I take all of the weight vectors of all of these student neurons across the n networks. I cluster them, for example, on L2 distance, and the results of this clustering will be big clusters of equal weight vectors neurons that happen consistently across networks because they're all at zero loss or close to zero loss. So a cluster for a neuron type 1, teacher neuron number 1, teacher neuron number 2, a few smaller clusters of zero type neurons, and one big cluster of constant type neurons. So the main idea of expand and cluster, I'm not going into the details, but the main idea is that since all of the student networks, they will be trained to reasonably low loss, they will all learn each teacher neuron at least once, while all the other neuron types, they have no reason to cluster because they're not shared between networks, except for the cluster of constant neurons that are very close to 0. So the bulk of the algorithm is just to fix a threshold on the size of the cluster and just keeping the size of the cluster that are close to the size of how many networks actually I trained and filter out the rest, so the red ones. And then it's easy to identify this cluster of zero-type neurons because they all point in arbitrary direction. They're very close to the origin, but they point in arbitrary direction, so they don't share a specific angle. And then the final step is to collapse each cluster into one single weight vector. You can do an average, you can pick the best or the neuron that was coming from the best students or the lowest loss. I think both of the policy work reasonably well, so they're quite interchangeable. So once you've done that, each cluster becomes a new neuron in your new reconstructed network. You can take this network. Sorry, well, let me recap. Basically, we train student networks that are of the same size as the teacher, and we get to very bad losses. Then we do some expansion, some overparameterization, and these student networks, they learn to get to even lower losses. And these student networks are actually closer to the global minimum. I can cluster all of the input wave vectors and collapse them all in single neurons. So I go back to the original size of the teacher, because basically I found 4 clusters of student neurons. And then this size 4 neural network can be fine-tuned in order to reach the global minimum. So this detour by expansion and clustering allows us to, with expansion, to reach a lower loss, which is basically close to the global minimum. And then the clustering just allows me to filter out all of the redundant neurons that I showed you coming from this game that we played in the theory. And then via simple fine tuning, we can actually find the lowest point in the loss. So I see there's a message in the chat, maybe. Can I open it? If you want, I can answer now. Yes, so the question is, do you overfit all the runs on the dataset before clustering? Yes, I do. So the idea is to train on the queries for as much as possible until you get to the lowest loss possible you can reach. So the lower you get, the easier it will be for the clustering procedure. Yes, so in a way, if you want, it is overfitting. We want to fit the dataset as best as possible because we want to reach functional equivalence between student and teacher on any input, basically. So this can be done at different levels of overparameterization, and then you can see these stars are the reconstructed networks. They all have the same size. So the clustering procedure always finds 4 clusters, and then they manage to reach the global minimum. So I told you there was a weird condition on the activation function, but actually to apply this theorem to more interesting activation functions, we have to include more symmetries. So for example, ReLU, I think we all know that it's a piecewise linear activation function, and there is a positive scaling symmetry, which basically consists in multiplying this scalar input here is the same as multiplying this positive scalar input on the output weights. So we lose 1 bit of information about the scaling of the input or the output weights. There are other symmetries that are a bit more interesting. For example, most of the activation functions are actually composed of an even plus linear part, meaning that the activation function is actually, you can decompose it as an even activation function that doesn't care about the sign of the input weight and an even component. So just to go a little bit more in detail, what is an even plus linear activation function? For example, ReLU, I can decompose it in this way. Soft plus, which is the integral of a odd function, sigmoid, and also JLU, which is linear times odd function, so it becomes an even function. And let's look at this again. I think it's interesting. So this happens only when you have overparameterization, when you have more student neurons to replicate fewer teacher neurons. So let's try to have 2 student neurons that sum together, but they learn the very opposite input weight vector. And if you just compute the sum, you know there will be a linear contribution where the 2 weights actually will subtract while they will add with on the even side. So the even side of the activation function doesn't really care about the sign of the weights. And it turns out that if this A1 plus A2 is actually summing to 0, then the contribution of this couple of neurons or group of neurons will be just a linear function. And I call it a linear group. While if this is not 0, then most likely these two neurons could even duplicate a teacher neuron, but then we will lose the certainty or about what is the sign of the weight vector, because there will always be another linear group that can compensate the function of these two neurons. I hope it's clear. So with this new symmetry that is actually common to many activation function, for example, you can learn two neurons of opposite weight vector signs with respect to the teacher that summing together with a linear group, so 4 neurons in total, they will be able to replicate one teacher neuron. And so just a simple visualization example for ReLU is very easy. You can see it. If you add a linear function, you can just flip the weight vector of the ReLU. So if you want to learn a teacher that looks like this, you can also learn it in this way. Good. And then the very final one is for odd activation functions. This is very easy. You can basically learn the opposite input weight vector here and then flip the sign of the output weight vector, and then you will have the same function. So there is an extra symmetry, which I call duplicate opposite group. So overall, there's a plethora of symmetries that come from different activation functions. So if you have even plus linear activation functions, you have to be careful because you will lose information about the sign of the input weight vector, because both of them are interchangeable. And the same goes for odd activation functions. While for ReLU, other than being even plus linear, there's also positive scaling. So you can also lose 2 bits of information in this case. So just to show a few results, I didn't go through the whole procedure of expand and cluster, but it also works for deep networks. The procedure is exactly the same. You can just, instead of reconstructing all the layer at once, it's better to reconstruct from the bottom layer. So you can train your deep teacher, your deep student, reconstruct and cluster the first layer and treat the first layer as the input to the second, and then kind of stack the procedure. And for example, here I trained a deep teacher of this size. So 3 hidden layers of 30 neurons each, fully connected on MNIST. And then I trained some students that have the same size as the teacher. They don't actually manage to get to a good imitation loss. So there's a very high root mean square error. But if I overparameterize, you can see that they can land to very lower losses. And then after clustering, we can almost identify exactly the same size of the teacher, except for 4 neurons extra in the very last layer, but we can really reach a lower loss. And on top of that, well, here I tried on many different activation functions. These are shallow networks, actually. And on top of computing the loss, the reconstruction loss, we can also compute the distance, the average cosine distance between the learned, the reconstructed weight vectors and the closest teacher weight vectors. And usually this is around 10 to the minus 4, 10 to the minus 5. So the cosine distance of my student weight vector with respect to the teacher weight vector is on the order of magnitude of 10 to minus 4 in cosine angle, which is very low, I believe. And just to conclude, I'm running a bit late. Why not just pruning, right? We took a very big overparameterized students, and we know that it goes to actually 0 loss because it can learn the teacher. Why, instead of training n of these guys and clustering, why don't we just do pruning? Well, we tried with different techniques, spanning from Lotte-Retica hypothesis, the classic magnitude pruning, and some more convoluted structural pruning when you can actually prune units. And what you can see here as a function of mean square error and excess parameters, as we go on in pruning, so from left to right, we actually managed to prune some neurons or some parameters from our student networks, but always at the cost of losing some loss. By the time we arrive at 0 excess parameter, so the same size as the teacher, our loss is basically useless. It's almost random chance. while expand and cluster actually lands here. So we effectively managed to break the Pareto frontier just because we have knowledge about the weight structures that is not incorporated in these algorithms. So to conclude, what expand and cluster simply does is takes a problem that is not solvable in the original parameter space, expand this parameter space by relaxing it, and by doing so, we are able to find the global minimum of this problem, but then we just need a way to project back the solution to the original parameter space. And this is done by clustering. So yes, the detour of expansion to clustering avoid non-convexities. I don't claim it's convex problem, but it's probably way easier, so more relaxed. And we also characterize in the paper all of the possible symmetries that I just briefly mentioned to use isomorphisms between bigger students and smaller teachers. And then we can identify hidden layer sizes and teacher weight vectors up to a sign or scaling factor, depending on the activation function. And with this, I conclude. And if you have any question, I'm happy to take them.
Thank you so much for the talk. Let me stop the recording.